Let's look at an example of how the past climates have been looked at using one particular model from NCAR in Boulder, Colorado, USA, called the Community Climate System Model. It became it has now become Community Earth System Model, so it just depends on the details that were added. But this is showing here the relation between global mean surface temperature and atmospheric carbon dioxide concentration in the model. The red dots show simulated global temperature response to rising CO2 concentrations based when using modern geography, ice sheets and vegetation. So in the model you can obviously change continental configurations, ice sheets, CO2 concentrations, all sorts of things, right? So that's the use of these, and you can see that the red dots goes like this. In the modern climate, basically if you increase CO2 with the given configuration, we're going to keep increasing the global mean temperature, which is what has happened since the Industrial Revolution, onset of the Industrial Revolution. The green dots show simulated global temperature response to rising CO2 concentrations when using modern geography, but Pliocene ice sheets and vegetation in the model. So you can see that the sensitivity of the Earth system during the Pliocene ice sheets is over here. We have already talked about climate sensitivity, and that's the range of temperature that we expect from the model, which has to be validated against observations, which is the purpose of doing these exercises. So during the Pliocene, the geography was essentially the same with little bit changes in Australia and the Himalayas and so on. We talked about the Pliocene, Pleistocene transition from permanent El Nino, so-called permanent El Nino, to the current intermittent El Nino. And the blue dots show the simulated global temperature response to rising CO2 concentrations when using Eocene or Cretaceous geography, which was quite different. No ice sheets because it was the Cretaceous warm hothouse which had melted away. There was no glaciers on Antarctica, Greenland, no Arctic sea ice. Siberia was lush green forests, dinosaurs running around and so on. So that is up here with high CO2 concentrations and high temperatures. So obviously interpreting past data with these models then becomes easier, because just the data do not give us all the process details, but the model simulation that can reasonably capture the parameters of the time, like temperature, sea level, or whatever other evidence we have, can help fill the process understanding, which is what I said before. So Earth system models are not just for future projections, but also to understand past climates, either for intellectual curiosity or for looking for paleo analogs to our global warming situation. So this is a conceptual schematic of an Earth system model compared with a traditional atmosphere ocean coupled general circulation model. Red arrows here denote interactively coupled components, and blue arrows denote where the data has been prescribed. So if you think about a coupled climate atmosphere ocean land model, then greenhouse gases and aerosols tend to be typically prescribed. So they may be varying season to season, year to year, based on observations, but they are not interactively, they're not prognostic, they are not changing with the climate, they are just prescribed. Okay, then you have coupling between atmosphere land and atmosphere and ocean. There should actually be an arrow here as well, which is the case for most models, especially the ones that are really the standard ones or the good ones, especially used for seasonal to interannual climate predictions, for example. When you do more Earth system kind of approach, you are going to add chemistry and physics, so this is not a diagnostic or prescribed quantity anymore, and you still have atmospheric physics and dynamics, but here you are going to add some sort of soil biogeochemistry, maybe dynamic vegetation or prescribed vegetation which is interacting with the water cycle, biogeochemical cycle, so the biophysical and biogeochemical feedbacks that we talked about with either full dynamic vegetation model or a simplified vegetation model. Ocean physics also would include biogeochemistry and in many cases sea ice, which so they all then begin to interact with each other. That's the idea of the Earth system, which we are starting off simply here in terms of a schematic. But we will see more details. So the IPCC process itself, which started doing projections, has been evolving with these models, but the historical evolution of climate models in the 1970s, they began to worry about the carbon impact of CO2 because the killing data was already making it obvious that warming was beginning to be registered and manifest, but many times they were just prescribed, not a interactive component. Mid-90s, you started to add land surface, and in the 1990s, we started to add a simpler ocean, and the 90s we started to add volcanic aerosols. In 2000s we added carbon cycle, more atmospheric chemistry, and so on. I'll keep it there because I'm getting a phone call. Let me continue in the next podcast.